And we're happy to guide you through in a little bit of a longer session about custom components for TensorFlow Extended. I'm here today with Timo Metzger. He's a wonderful technical writer with a background in journalism, and he supports a lot of data science projects and currently is supporting the Bokeh project with technical writing and sort of the outside world assistance, I would say, that the data scientists develop tools which are useful to a broader community. And Timo has helped for various projects in the past, and he's like a wonderful person to work with. So thanks Timo. Thanks for joining today.
Yeah, thanks a lot. Yeah, I'll be mainly just trying to manage questions, make sure you get the answers you need, and be moderating a little bit. So ask away optimally right here in Zoom. That would be great so we can see what's going on. Thanks a lot.
Cool. So we have if you want to follow along, here's a bit.ly link. It's custom TFX components. You can see the notebook we're walking through today. This is a slightly different session, so we're not going to do exercises because there's quite a lot of content we have to go through in order we can run our pipeline at the very end. But I want to make sure that you leave the session today with the key understanding of like how custom component work in TensorFlow Extended and how to use your Apache Beam knowledge to A, build components, and then B, to orchestrate your pipelines. So at the very end, we're going to have a complete pipeline. So a couple of things here. Let me switch the screen sharing and switch to the notebook. So here we are in this notebook. This is something, again, if you want to follow along, feel free to do that. There's an open and collab link on the top. You can copy that. If you just want to listen in, that's also completely fine. Feel free to raise questions whenever you have some. That this should be, as much as we can have it, an interactive session. So before we get into the details of like how to build a custom component for TFX, let me just briefly introduce TFX for anyone who's new to the concept of TensorFlow Extended. So the purpose of TensorFlow Extended is to build machine learning pipelines for machine learning problems. So we know pipelines for ETL processes, for data. We know that for software packages. Machine learning pipelines are a bit different because they are less linear. Even though the flowchart here shows like a linear pattern, but in the machine learning world, we reuse artifacts from a couple steps behind, and we push them to a couple steps ahead. So it's not like a linear process as we would have it in the CI/CD systems for software. The wonderful thing is TensorFlow Extended gives us individual components for each of the different tasks. So for example, everything in the machine learning world starts with data. So we need to ingest the data. We want to validate our data sets. We want to pre-process the data sets. And then once this is done, we want to start training our machine learning models and then analyze the machine learning models. And if everything works fine, we want to automatically deploy them. And TFX gives us the opportunity to write those pipelines and then also orchestrate them on different platforms. This library, or this portfolio of libraries of what we call TFX today, has grown substantially in the last couple of years. And so what has happened is that now we can even integrate like custom orchestrators and custom components, etc. So as you can see here, we have those blue boxes. They are standard components in TFX. That gives us a wide range of functionality already out of the box, but sometimes we want to go into a little bit more details. For example, we would like to build custom components to communicate pipeline results. We would like to potentially generate new pipeline artifacts like model cards or other summary statistic tools, or sometimes we just want to ingest different data types which aren't supported out of the box from TensorFlow Extended. And that's what we're going to focus on today in this workshop. I want to guide you through the process of how do you build a custom component to ingest images in our case, and convert them into something we can reuse in our machine learning pipeline. All right, so quick overview of TensorFlow Extended. I've already talked about this briefly. We started talking about this a couple minutes ago, but here, quick overview again. So in 2016, 17, or I would say 16, I'm not quite sure on the exact date, TensorFlow Serving was published, or was open source. That was the first product of that TensorFlow Extended portfolio. And then more projects came out, got released as open source projects, but all as standalone projects. So we had like TensorFlow data validation, we had then TensorFlow transform, TensorFlow data analysis. And then last year with the Dev Summit for TensorFlow, Google released the glue code between those components, and that's what we call today TensorFlow Extended or TFX. And all of a sudden, we were able to use the functionality of TensorFlow data validation as part of different components. And we can now arrange those components into pipelines and then orchestrate those pipelines so that we can run those machine learning pipelines automatically and continuously if we want to. And this is going forward, this is going to be a game changer for a lot of companies. All the data science work currently is maintained manually, and we need to free up the data scientists' time to let them focus on the innovation part than rather maintaining existing models. So this was also the key motivator why Catherine Nelson and I teamed up and co-authored a book called Building Machine Learning Pipelines. This got recently published by O'Reilly, and this explains an end-to-end example of how to build machine learning pipelines, but we also go a step further. We talk about machine learning privacy, we talk about machine learning feedback loops, we talk about federated learning, and all these different aspects which are surrounding machine learning training aspects. So if you're completely comfortable with training machine learning models, then this is the perfect book for you if you want to sort of see how you get your machine learning models into the real world and automate your model creation. So, but the talk today is not about machine learning pipelines. The talk today is about TFX components. And so I want to give you a quick overview about how a TFX component works in detail. And a big shout out here to the TensorFlow team or the TensorFlow Extended team. They have done an amazing job in building a framework which is highly extensible, but also highly consistent. So each component, regardless of what component it is, consists of three parts. We have a driver, we have an executor, and a publisher. Parallel to our pipeline, we run a metadata store. And the metadata store will track the references of all the artifacts consumed or produced by a component. So that means that, for example, if we start up a component, the driver will look up all the inputs which we hand over to the component, and then get the actual references with the values from the metadata store, and then pass them to the executor. The executor contains the actual functionality. So basically, for example, in our case, we want to load images from a folder. The driver will basically get the information about the path where all the models are, or the images are, sorry. Hand the path over to the executor, and then in the executor, we basically generate a list of all the file names, loop over all the file names, turn them into TF records, save the TF record file, and then the reference of the file itself will be handed over to the publisher, and the publisher communicates it back to the metadata store through a gRPC service. So highly consistent, very, very structured. How can you build your own custom components? There have been major changes in the last couple months. And again, a big shout out to the TensorFlow Extended team here. Timo and I were not working for Google, but we're on the outside. So we're heavy duty users of TensorFlow Extended. I work at SAP Concur, so we use TensorFlow, and I've used it in other settings. So I can tell you sort of like the user perspective here. And there have been tremendous changes in the last 2 months in terms of how we build components. So first of all, we have now a new decorator. With the decorator, we can decorate functions, and the functions then basically represent the executor functionality that heavily relies on typing. So in typing, we define what are the inputs, what are the outputs, because we get those different types for our component. And then we can basically write the functionality and return the results. That is the simplest and straightforward way of like writing a component today. Then we have a second approach that is called the component-based components, or container-based components, I'm sorry. The great advantage here is it is language independent. So you can write this, for example, you can write the component in Rust or in Go. As long as you can stuff everything into a container, you can then call that image and you can specify the inputs and the outputs. And for that, we can specify your URI or value placeholders as inputs and outputs, so the container knows what needs to go back and forth. And then we can integrate that component, that container component, in our pipeline. So if you have some code and you want to run this maybe in a different language or in non-Python code, then this is a perfect way of like how to build components and integrate them into your pipelines. And then we have a third approach, which used to be the only approach previously, where we would build, sorry, I scrolled too far. We would have to implement our components. And so that's what we're going to talk to today. It's also the most complex implementation and requires the most understanding of what actually happens inside of the components. So I want to focus on this today. The other two options I just mentioned earlier, they're easier to adopt. But for example, if you want to inherit functionality from existing components, or if you completely want to rewrite a component from scratch, I highly recommend the third option, and we'll go through that in detail here in the next couple minutes. So generally, we have two options. We can write the entire component from scratch. In this moment, we have to write a component specification. We'll go through that in detail. And then we have to write a driver and the custom executor. And then we wrap everything together in our custom component. We will see that there's a lot of boilerplate code involved. And I will also walk you through a second approach where we write a component, but we reuse existing components already, and we swap out the executor functionality. Hang on, I'll walk you through those examples here in a couple seconds. If we're walking through this whole thing here way too fast, no worries. You can always ask questions. You can connect with us on Twitter. There's also wonderful TensorFlow and TFX documentation. The TFX documentation has been revamped drastically in the last couple of months, so that's really wonderful to see. And again, big shout out to the team there. They do fantastic work. If you want to read this in a non-digital way, I highly recommend the publication we just published here 2 months ago. So you can read about pipelines cover to cover, maybe somewhere in a hammock or in a non-digital world. Today in this workshop, just quick outline. We download the data set here. I'll walk you through the quick installation of this one package we need. It's pretty simple. We then define some helper functions. And I'll walk you through the implementation from scratch. And then there will be some deficiencies in there, and we'll remove them by implementing that through the second approach by overriding an executor. And then I'll show you how to convert this back into the Apache Beam pipeline, which you can then orchestrate with Apache Beam. All right, so let's get started here. So for today's example, we'll classify cats and dogs. We'll train a machine learning model for this. And the reason is it's an image data set with a lot of computer vision problems. We want to ingest raw image data and pipe them directly into our pipeline. The reason why we would like to build a component here is because if it happens in the component, we generate the metadata in this moment automatically, and you can see which images have been used, or which raw folder has been used to generate the model later on. If we, for example, would convert images to TF records outside of our pipeline, then this would sort of cause the data would be not tracked in the metadata store. It would not be part of the model lineage. So we basically, by integrating this into the machine learning pipeline, we can orchestrate this piece, and then we capture all the additional information. All right. So what I have done here also, just a quick note, if you want to run this through this notebook yourself, I reduce, in the interest of time, I reduce the number of images here. I just keep 500 dogs and 500 cats. If you want to run through the entire pipeline and do some stress testing with 25,000 images, just remove those 3 lines I've highlighted here, and then you get the full exposure of the entire data set. All right, quickly installing here the packages. The only package we need is our TFX package. This has been also, there has been a lot of changes in the last couple of months. Most recently, the Apache Beam version has been upgraded, and there's a lot of, that brought in a lot of amazing functionality into TFX automatically. For example, now we can ingest data directly from S3 buckets and things like this. This wasn't possible before, I think, Apache Beam 2019 or something, 2019. So I'm very excited about this additional functionality. All right, so while this is running, this takes a few more seconds here. In Colab notebooks, once we install packages, we always need to restart our session. We can either do this by going through runtime and then restart runtime, or we can do this programmatically. We can basically kill the session, and then Colab is nice enough that it automatically restarts the Jupyter HubNet session behind the scenes, and then we get a new, we can load our packages here. So here I'm importing all the packages we need to execute the entire notebook. Not everything is needed to build a component, but there's additional packages here we need later on to run our pipeline, for example, the Beam runner, the Beam DAG runner, which we'll see later on. Okay, quick note, I'm reducing the log level here. That is, some of the components are highly verbose, and there's so many log messages that Colab crashes. Therefore, I just reduce the log level here. Nothing to worry about. If you want to run this in production, I highly recommend to pipe those log messages to some additional, to some log file or something, and then everything should be fine. So in order to write our component, I need some helper functions, and let me walk you through those helper functions real quick. So we need when we train a machine learning model, we have those images, and we need some labels. Obviously, it's supervised training, so we need some sort of labels. I cheat a little bit here. The data set is already sorted or into folders. So we have a folder with cats and dogs. And so what I'm doing here is I say, if the word dog is part of the path, then give it the label 0. If there's a cat in the path name, give it the label 1. And then we use those integer labels later for our machine learning training. In TensorFlow, when we generate TF records, it is expected that the TF records contain TF example datasets. And those TF example datasets, again, consist out of TF features, which we're defining here. So in this case, we're defining an integer feature. This is going to be reused per our label. And we define a byte feature, which we then use to represent the byte string of those images. So that's what we're going to do here. This is basically in line 50 through 55. This is how we define a TF example data structure. Again, we give them the name image raw, and we pass the byte string in there, and then we pass the label over. All right, and then we generate a function which will reuse in our components or component, which is basically we pass a single file path of that file name over to that function. We generate the TF example data structure. At the same time, we generate the label, and then we convert that image to a byte string, pass it over to a convert example method, and then receive a TF example data structure. All right, with those functions here in place, then let's talk about how do we actually now build a TFX component. So before we get into the code, a couple highlights here. So we have a component, and the components, they communicate through channels. And so a channel would be a piece of information, what comes from the metadata store and what goes to the metadata store. And again, we're not storing the images, we're not storing any data or models in the metadata store, we only store the references. Okay? So then we define component specifications. This is basically the blueprint of our component. We say, these are the inputs, these are the outputs, and then we have what is called execution parameters. So we have input channel parameters, output channel parameters, and execution parameters. And the difference between the channel parameters and the execution parameters is that we track the channel parameters in the metadata store. And for example, additional information which we pass to the component, like for example, the name or a split ratio or things like this, that is being passed in as execution parameters. We can still track them in the metadata store, but it's not like data flowing back and forth. All right, and then, so basically we compile our component specifications, and we can always, there's a lot of already existing functionality. In this case, we inherit from the component specification provided by TensorFlow Extended. And here we define our component specs. We say, as an execution, the only execution parameter we want to provide in this component, just for simplicity here, that is the name. We generate the input. We call this also the input, and then we call the output examples. And that is sort of like the nomenclature of what has been reused, has been used by other ingestion components, like the import example gen or the CSV example gen, so that in that way we stay consistent with what is already existing out there. One second. All right. So once we have defined our component specs, let's focus on the biggest part of our component. We can now focus on the executor. And remember, we have already created our get image data function, which accepts a file path, converts everything, generates the label, converts everything into the data structure we expect. And then the return from that function is a TF example data structure, which we then can write to TF records. And currently, components communicate the data in the TF record data structure. There is an RFC open to change this to a different data structure, but as of today, this is the underlying data structure. So then we have our input here, and the input is an external artifact. And in TFX, in those ingestion components, it is expected that we pass in pass in the folder where all the data is living. This could be a GCP bucket or an S3 bucket. We don't pass in like a list of file names. That's something that the component itself will generate. So in this case, that's what we do. There's also the components generate in protobuf data structures, but TensorFlow Extended gives us a lot of functionality to extract and to read those protobufs and read those different data structures, to use them in like generic Python data structures. So for example, here we have our input dictionary. We take the input key and then read the base path of our input data file or data folder out from there. So we use the TensorFlow functionality to generate the list directory. So this gives us the list of all the file names. And then to avoid that we train on only dogs and then cats, we shuffle the list. That's basically just a little bit of randomness in here. We split our data set. Our data set is not split into like a training set and a validation split. That happens inside of the component. And so in this case, it's a very simple implementation. We say the first 100 records, they become our evaluation set. This all the remaining records or all the remaining images become training images. And so then we create a list of tuples here where we say this is our splits. And then basically we loop over that list of splits, and for every split we generate a TF record file where we go through all the images and write them to our particular TF record file. So that we then can store and use in the downstream processes. And when the information of the component is headed over to the downstream components will be aware of the split and our eval and training split, and then use those information later on. You will see this here in a second. There's one tweak. This is an ingestion component. So basically the first component of our pipeline. That means that we have to manipulate our driver of our component a little bit, because we are not receiving information from another component. So the data which is being inputted to the pipeline has not been registered with the metadata store in that moment. So that's what the driver takes care of. So in this moment, we basically override the existing functionality. We have our input here, we have our input channels. We take the input dictionary. This only contains one value in our case. And then we register this when we say publish artifacts. We register this with the metadata store, and then it is registered and then can be used for downstream components. And then we have a complete model lineage. All right. So then the very, very last step, we have now built the component specifications. We have built the executor, and then we have built the driver for our ingestion component. You don't need to override this with downstream components unless you really move away from the standard structure. But now with all those things defined, we can put this all together in our custom ingestion component. So here, we override this the specification class, we override the executor and the driver in our case, and then basically, if no output data is defined, which is the case for us, then we say the output will be an artifact which represents TF examples, and we have defined our split here as training and evaluation. We register this with the artifact, and then we can say we want to register this as an output channel, and then we pass this to our ingestion specification and say we have our inputs here, they're provided from outside of the component. The output will be generated by the component itself, and then we have our execution parameter, which represents the name. So long story short, we now have to find our very first component from scratch. So how does it look like if you want to use that? So very, very similar to how you would use any other component in TensorFlow Extended for data ingestion. So we define, in this case, we use the interactive context because we're running this in a notebook. And we also, in this moment, the human is the orchestrator. So we'll just execute cell by cell. We define our data root, and then we define this as an external input. This behind the scenes creates a protobuf definition of the data is then being passed over to the component, and we can then execute our custom ingestion component. So if we execute this, then let me show you what's, if I haven't forgotten to execute a cell, ta-da, this works. So we now ingested our images of the dogs for the simplicity here. And now let's take a look. We execute a downstream component, In this case, that's our statistics generator. We see that we have loaded 501 images in total. There has been a split. So initially we said like we take the first 100, they become our evaluation data set. We said that we only load dogs in this case, so we have 100% of all our labels are 0. So this has worked. And then we see that we have 401 unique byte strings. That's also great. That's good to know that we don't load in for some reason images twice. So now we could potentially pass those images to TF transform, train our machine learning model, validate it, et cetera, et cetera. This was a lot of boilerplate code. So if I go back to the component, I think this is, there's a lot of shortcomings here in the implementation. And I just want to show you in the next step of like, how can we write less code and then make this more adaptable for your component execution. So for example, here in the pipeline itself, we defined what the split is between training and evaluation. We also defined that we only accept training and evaluation setups. So it would be nice if we could define this in our components and say, we might want to have a test set, or we might want to have a different split. And TFX already supports that. It would be a lot of like implementation to write the functionality from scratch again. So let's take a look at how we can provide a new component by overriding an existing component. And that's basically what we do in the following example. So in this case, we don't write a driver, we don't write a custom specification. And I have to admit, I have to be really clear here. This approach works if there is a component existing already in TensorFlow Extended, which uses the exact same inputs and outputs for your model flow. Let's say you want to change the functionality of TFMA or TensorFlow Transform. This is something you could potentially do, and we'll do this here with the file ingestion component. So all the components, for example, the TensorFlow record ingestion component or the CSV ingestion component, is based on the file-based example gen component. So we can take this file-based example gen component and then add the functionality in our model or in our component, and we don't have to write the component specification, and we don't have to write the driver. As you will see here in a second, much fewer lines of code, much easier to maintain, less brittle, higher flexibility. So in this case, we have to write a function, which we call here image to example. And this and this is where Apache Beam comes in. This takes a pipeline, and then we can process the data on that pipeline. So for example, we have split patterns, we have execution properties, and we have our input directory. This is the basic setup for any ingestion component. So that also means we can then downstream, or in our pipeline configuration, we can also then use the standard TFX settings for how we want to split our pipeline, how we want to load our pipeline, our ingestion to the pipeline. So then, very similar setup. We load the artifact. We get our base URI pass out of it, and then we determine the patterns. And so pattern means, as we'll see in a second, we define how do we want to split the output. That's something we do not in the component. The definition, we do this in the pipeline itself. Maybe you have a pipeline where you say, I want a training, eval, and test set, and then you have the next pipeline where you say, just want training and eval, and that's something you can define in the pipeline itself instead of the component. And then the beauty is because we can we can use Apache Beam. So all the Apache Beam knowledge we have, we can apply this, and we can then return a P transform as the output of that function. Because the wonderful functionality here is then we can basically, in this case, we have our helper function, which I introduced before. We can then execute this and map this over the entire list of files. So up here, we generate all the file images based on the patterns. We get all the image file paths of our cats and dogs. And then we pass this to Apache Beam. We can distribute the image ingestion and then also the conversion that we can run this on Apache Beam and whatever runner we use. So then the beautiful thing is we can reuse the base example gen executor and basically overwrite the functionality. And that base example gen executor expects a function. So if we want to use Apache Beam to distribute the conversion or the data ingestion, then we need to override the get input source to example p transform function, quite the function name. And we just override it with the function we defined previously. Let me quickly jump back here because there's something I want to highlight. This is this decorator. This allows us to simplify the way the decorator basically behind the scenes defines the p transform, and that replaces the standard expand function which we would have to define in Apache Beam. All right, and then with this component being defined, we can then create our new pipeline. And here, this is the standard TFX definition. So we define our inputs. So here in this case, we want to read all images, or that's just the name, but from this base path, and this is our base path, the pet images folder contains two, I can show you this real brief. We're in here, this has a folder with cats and dogs. So then we take all the JPEG images of one level below. That becomes our pattern. And then in our TensorFlow extended definition, sorry, that jumped up here, we want that the component outputs two data sets, and we want to split them with the name train and eval again, but with a split 1-4 instead of the first 100 images go in one bucket and then the remaining ones go into the training bucket. So if we define our components here, let's execute the component. In this case, because now we're loading cats and dogs, we'll see the double of the amount of images. So let's take a look at the statistics here. We ran the component. We now see that we have roughly 800 images, so it's like 80%. If we have a 1-4 split. So if I scroll, oops. Oh, the eval split wasn't possible to display that. But at least we see like it's exactly a 50% split. So we have 50% of the images are cats and 50% of the images are dogs. So I'm not quite sure why the eval split is not currently displayed, but let's move on. Let's see what the schema says. So in the schema we have, we see our input types or our features here. We have the images, we have the raw images and the labels. We have the example validator, so in case we see any deviations in our pipelines, that's what the validator would basically highlight and say, hey, here's a problem. We then, let's run this. The next step in our pipeline would be TensorFlow transform. In the interest of time, this is like a really high level of our pipeline here. I just want to browse through this to show you the fine functionality. But basically what we do here is we define our feature transformations in our pipeline. So we take the raw images and convert them into something we can then use in our model training. And so in this case, we read each JPEG image. We normalize the image basically by centering around 0, and then convert this into a float value. And that's often standard pattern for computer vision models. One key thing here, since it's people always ask me, why should I use TensorFlow transform? I can pre-process my data maybe in a Python script beforehand. The big advantage is we can during the training process, we can generate a transform graph. And then when we export the model later on, I will show you this in a second, we can then export the trained machine learning model together with the transform graph as one artifact. And the big advantage is, at this moment, we avoid that those pre-processing transformations become out of line with the trained model. So we can avoid training servant skew in that moment, since they're basically being shipped as, or they are shipped as one artifact. Okay, so we transformed our 1,000 images here, or yes, so we transformed our 1,000 images. We also generate the transformation graph, which we will then reuse in a second here. And then if we, for example, serve this with TensorFlow serving or KF serving, we can then send the raw images to the model, and the model will pre-process them and then classify them. So there's a lot of amazing functionality we can build into TensorFlow Transform. If you're interested in that, I highly recommend taking a look at this package, especially with like computer vision problems. We can resize images, we can normalize those images inside of the model, and that helps to prevent, like as I said earlier, the training servant skew. Okay, then we actually get to the bread and butter. We have a little machine learning model here. So I'm not going through all the little details here, but we can basically train a mobile net model to detect the cats and the dogs. And then we basically have a single output node where we say, is it a cat or is it a dog? When we export that model, all the input will be passed through that's served to TF example function. And so in this moment, we take the raw features presented to the, or coming from the transform, and then we take the data passed through the model and pass it through the transform layer we just generated in the previous components. And again, when we export our machine learning pipeline, this whole process will be automated, and we can continuously update our machine learning models without any intervention by a human if we want that. And so we could, for example, every day generate a new machine learning model and deploy that. Okay, so we define our model here. There's a lot of boilerplate code in there. If you're familiar with TensorFlow Keras or TensorFlow, there's nothing new in there, I would say. And then we can define our trainer in our pipeline and say we want to train our Keras model here, take the transformed examples, which we just generated in the previous step, reuse the schema we generated earlier. That's why, again, it's an example here that our pipelines are not linear, because a lot of artifacts are being used from previous step. And then we want to train this, in this case, just for the interest, 1,600 steps or 160 steps, and then 200 steps for the validation. Obviously, that's just for demonstration purposes here. If I want to show a pipeline, then, or if I want to train this pipeline in production, that will be significantly longer. While this is training here, any questions from the audience?
So far, no. We just have greetings, but no questions so far.
Okay. That training should be done here in any second. I can already talk about the next step here in our pipeline. It's really critical. When we train machine learning models, a lot of data scientists say, oh, I trained my machine learning model. I saw that the accuracy is 97%. I see that the loss is low. Let's push that model out and deploy that. But I think we need to be a little more careful. And TensorFlow Extended gives us a wonderful tool, which is called TensorFlow Model Analysis. So we can push our newly trained machine learning model through specifications. So we can say, let's look at, for example, the area under the curve, or let's look at the F1 score or recall and precision. We have all all different metrics available. And then in this case, we don't perform this, but we can also slice our input data or validation data by a certain feature, for example. So for example, if like we have photos from Android phones or iPhones, then we could, if we have this as a label, we could slice our input data, and then we can, in the validation step, say, what's the performance for all images coming from an iOS device, and what's the performance for Android devices. And if there would be, for example, a big deviation, then we could say, stop, let's not deploy this model. But this is basically what we define in our eval config of like what is acceptable, and then what is considered a good model, what's considered a bad model. There's a lot. I think there's a whole talk can be given about those configurations. We can give threshold levels. We can give like change levels. There's a lot of. So this is only the basic configuration. Then we can also we have a resolver node, which is basically allowing us to look up data in the metadata store. And in this moment, we can look up how was the last model performing, and then we can compare our evaluation results against the last model, and we can say that model is X% better. And then we can also define like how much better is that model. So there's a good functionality we can include in our machine learning pipelines here. And then finally, after all this configuration, we can then execute our evaluator. And this takes a little bit of time because it goes through the 200 examples we generated. And it generates those reports. And then basically later on, if everything worked, so we can then visualize the data. I haven't configured this like extensively here, but for example, if I would put in a split by labels or by cats and dogs, we can then see how the model is performing. I didn't generate any F1 scores of false positives, false negatives, and so on. But that is something we could expect here. At least in this case, we see what the AUC would be for our 204 evaluation samples. And then as a last step, we can deploy the machine learning model. And deploying this, in this case, means we can push that model to an outside location, and then a machine learning model server can pick it up from there. So for example, TensorFlow serving can continuously pull file systems or remote cloud storage buckets. So in this case, if we store this in a location where TensorFlow serving or Cave serving can pick it up, then we can automatically deploy machine learning models. So in this case, I think the model, so we ran the pusher. So this is basically the end of the pipeline here in this moment. Now the question is, like, in this case, I was the orchestrator. How can you use Apache Beam to orchestrate the entire pipeline? And so in the previous steps, we have defined all of these components. And so with a few base parameters, basically, where do we store the metadata? What's the pipeline route? Where should all the output artifacts go if we store them somewhere? Where's the base of the pipeline? We can then export all the components. So in this moment here, I need to sync with Google Cloud or with Google Drive here for a second. 1 second. So in this moment, we can automatically convert that pipeline we just defined in our notebook to something we can then run in Apache Beam. So for example, this is our notebook path. We just mounted my Google Drive into that notebook. We can then export this this component or this entire pipeline to Apache Beam. So then we have this exported Python file. And if I open this up, we can then, this executes Apache Beam at the very end with the entire pipeline definition. So if you have Apache Beam running somewhere, then you can execute this. I don't want to run this now in the Colab because it's really verbose, and Colab seems to die with so many log messages. But you could download the Python script, put it together with another module where you host the component, and as long as you have access to the cats and dogs images and the path lining up, then you can execute that pipeline. There's a question in the chat. Do I typically develop TensorFlow extended pipelines using the interactive context in a notebook, or is it more for demonstration purposes? How much do you use those TensorFlow data validation visualizations for TFDD and TFMA once your models are actually deployed? To the first question, I always start with an interactive context. Because there's like nitty-gritty details of like, are the paths all lining up? I also get immediate feedback. I can execute each individual component. I don't need to run entire downstream, the entire downstream pipeline. I can, for example, just execute from data ingestion to TensorFlow transform if I want to update my transform steps. So I always start with the TFX pipeline in the interactive context, and then convert this into something I can reuse on my orchestrator. Do I use the TFDD visualizations after the model is actually deployed? So I think once the model is deployed, I keep them as a record. So we store them in our metadata store. It's part of our model lineage. I think it's really, really critical that we keep those records. If somebody in 3 months comes in and says like, hey, I think this model misbehaved in this prediction, then I want to be able to go back to the metadata store and get the model lineage for this particular deployed model and retrace everything. I want to see which data did we use. I want to see all the data visualizations and model visualizations, because it helps me to understand the model. So we preserve them. But we use them interactively. So for example, we run our pipelines, our production pipelines with Kubeflow pipelines right now, and they have a nice setup where the UI is integrated. So we can click on the components and we see the visualizations. Obviously, we don't have that in the Apache Beam pipelines. And so in our case, we use those Apache Beam pipelines for debugging, if you want to test things in the pipeline setup. And it's also really good to execute sort of like UI free component pipelines. So sometimes we just have a gigantic EC2 instance where we want to run our pipelines, and then I prefer to use Apache Beam. There's another question, must the output of the custom component always be a TF record example? Currently, yes, that is the case. The downstream components expect TF records. So they, for example, TFDV expects, so the component itself expects TF records. As I said, the data structure might change in the future, but as of today, that is all the downstream components are using TF records. If you use, for example, TensorFlow data validation as a standalone package, as a standalone library, there are entry points where you can use CSV files or pandas data frames as inputs. But when we talk about pipelines, the data passes around in TensorFlow TF records. Any other questions?
One more question from Thomas Gaddy, who thanks you for the answers, and then has one more question. How does the trainer work when you orchestrate using Beam? Is the model training on the workers? What if you want to use GPUs?
That's a very good question. Thank you, Thomas. So in the trainer component, it basically, in the trainer component, it actually runs the training within the component. So for example, if we run this in Apache Beam, in Kubeflow pipelines, then that spins up a container and the trainer runs in that container. If we want to use GPUs, I can specify GPUs to the entire pipeline and say you can run all the pipelines on that GPU. Currently, we can only specify, so in TFX, we can only specify that for the entire pipeline, but I think there was a discussion somewhere on GitHub that this might change, that we can give container-specific specifications. But currently, as far as I know, I might be wrong, but as far as I know, that is pipeline-specific. If you orchestrate on Apache Beam, then the Apache Beam training, does it happen on the worker or scheduler? So in my opinion, it happens on the worker. I need to verify this, but that worker would have to have access. Wherever you execute that training code, that would have to have access to that training. But since we're like an Apache Beam, this is running on Apache Beam, we can also send it to Dataflow, or you can connect it to the AI Google Cloud AI platform. And let me go back here. So
DA was wondering if the URL for this notebook is available. I think Venkat already posted a URL, but maybe you want to point out where to find it.
Can you guys see the screen? That's the URL. That's the wiki shortcut. And with that, yeah, thank you very much for joining us today. And there are Twitter handles. So Catherine and I, we wrote the book about machine learning pipelines together. And then Timo is the technical writer for a lot of data science projects. So feel free to contact any of us.